Hello, for today's video lecture, we're going to be talking about work, kinetic energy, and potential energy for rigid body systems. So all of this is leading up to the work and energy method in kinetics, which is best summarized as this. The work done to a system will be equal to the change in the system's energy. So before we go too much into depth into applying this, we would need to clearly define what work is and what energy is in terms of what we talk about in dynamics at least. So work is going to be a force applied over a distance, or now in rigid bodies, a moment applied over an angle of twist. So I can apply work via a force or via a moment. Energy is going to be translational or rotational kinetic energy, or alternatively, it can be gravitational or elastic potential energy as a replacement for the work done by gravity forces and or elastic spring forces. All right, so let's go into more depth in each of these. So starting out with work. So the work of a force, and as we discussed this with particles, the work of a force will be equal to the magnitude of the force times the distance which the force is exerted over. So force times distance is the basic formula we have here. So W is the work, F is the magnitude of the force, D is the distance the force is exerted over. So it should also be noted, and this is talked about in more detail in the particle section, that only the component of the force in the direction of travel will do work. So if we have a force that doesn't line up with the motion, we're going to need to break that into components and find the component in the direction of travel. If we have forces that oppose motion, so friction forces often will do this, where the direction of travel is opposite of the force, that will do negative work on the body. So for forces with magnitudes that vary with position as well, so if the force is not a constant value, we can take the integral. So work would be the integral of the force function over the distance traveled in this case. So whatever definition of work of a force is going to be best for your situation, you're going to use that one. All right, so next up with rigid bodies, we have moments. This is the new part. So the work done by a moment exerted on a rigid body will be equal to m times delta theta. So where W is the work done, m is the magnitude of the moment, and delta theta is the change in angle of the body. So if it's exerted over, say, 1 radian of twist, that would be your delta theta. So this does need to be in radians for the units to work out. If we have degrees, it's going to give you some weird units in all this. And just as with forces and translational moment, the work of a moment is only the vector component of the moment that lines up with the axis of rotation. So if you've got a moment that doesn't line up with the rotation, you need to just take the component of the moment vector that lines up with the axis of rotation itself. And also, as with forces, moments that oppose rotation, so if you've got a moment that's due to friction, for example, that would be negative work in your equations. All right, so also as with forces, if the moment varies with position, we can integrate the moment over the angle of displacement. So we can go from some theta min to theta max, take the moment function with respect to that distance, and basically find the area under the curve using integration. So some things are going to have this, such as torsional springs, which the angle of twist itself is going to determine what the moment is from the spring that we get. It'd be a linear curve, not a curve like this in that case, but we will have to deal with that sometimes. All right, so it is important to note that since a single off-center force can cause a force and a moment, a single force can also do linear work and rotational work. So say, for example, like situation A, we're just pushing a box over a surface. That would just be force times distance for the work. In the second case, if I am pushing on the corner of a box here, I've got a force times a distance for my work there, and that distance would be the travel of the center of mass of the box. But I've also got a moment, so the moment exerted by that force times the angle of twist from some initial state to some final state is going to be the work done by the moment part of the force. So I'd get both components of that. So example B there, I'd have both a force times a distance and a moment times a change in angle. All right, so that wraps up work. Next, we're going to talk about kinetic energy. Specifically, we're going to start with translational kinetic energy. We talked about this already with the particle section. So 1/2 mv squared is our kinetic energy. This is m is the mass of the object, v is the speed of the object. So I have v for velocity, but we're just worried about the magnitude of the velocity. And magnitude of velocity is the speed. So in our conservation of energy equation, we use the kinetic energy, which is assuming a constant mass. So delta Ke is going to be 1/2 mv final squared minus 1/2 mv initial squared. So, and delta Ke is what shows up in the equations, not necessarily the Ke we have above. So final and initial velocities is what we need to distinguish. Rotational, we're going to have a lot of the same setup. So the rotational kinetic energy is the kinetic energy restored up in the relative motions of all parts of a spinning body. So if you've got like a wheel on or like a flywheel, we can easily think about this having energy. So as this thing is rotating, the center is not really moving, so there's not 1/2 mv squared, but all of the pieces around the edge of this, that will have a velocity. So 1/2, if we sum up all those 1/2 mv squareds of the pieces, we'd wind up with the following. 1/2 I omega squared. So I is going to be our mass moment of inertia, and omega is going to be our angular velocity. So we want to find, for fixed axis rotation, we want to find everything relative to the center of rotation. So everything in this case mostly being the moment of inertia, that IO, needs to be the mass moment of inertia about the axis of rotation. For changes in kinetic energy, we simply would do the following. So 1/2 I omega final squared minus 1/2 I omega initial squared. All right, so for general planar motion, where we got rotation and translation, the change in kinetic energy will be the summation of those kinetic energies of the two types of motion. So we'll have both rotational and translational. So 1/2 mv final squared minus 1/2 mv initial squared would be the change in translational kinetic energy. And then 1/2 I omega final squared minus 1/2 I omega initial squared would be my rotational kinetic energy. And in this case, the velocity refers to the center of mass of the object. So in here, my v final and v initial needs to be measured at the center of mass. And the other thing is the I values. So I over in the rotational part, our mass moment of inertia needs to be taken about the center of mass of the object. So this is for general planar motion where we don't have fixed axis rotation like we had before. All right, last up with kinetic energy, we can talk about the instant centers. So as an alternative to general planar motion, we can also use instant centers as a way to quantify the kinetic energy in the system. As this is similar to fixed axis rotation, we only need the angular velocities to deal with. And we'd have 1/2 I omega final squared minus 1/2 I omega initial squared. And I've got my final angular velocity, initial angular velocity, and the I in this case is going to be about the instant center. But one downside to this method is that the instant center will often change over time. Since the instant center changes, the mass moment of inertia will also change over time. So you might need to calculate separate I values for the initial conditions and the final conditions in a case like this. So we remove the translational terms, but we're possibly adding in another issue with the changing instant center location and changing mass moment of inertia. So whichever one works, pick a method, either instant centers or general planar motion, and stick with that for your problem. All right, so after kinetic energy, we're going to move on to gravitational potential energy. So in rigid body systems, the gravitational potential energy is much the same as it was with particle systems. So gravitational potential energy is not really energy at all, but instead represents the potential work done by gravity. So if we include gravitational potential energy, we don't include the work done by gravity. This is to replace that. So the change in gravitational potential energy for a body is going to be mg delta h. So m is the mass of the body, g is the acceleration due to gravity. It's going to be 9.81 meters per second squared on the surface of the Earth, or alternatively 32.2 feet per second squared if we're working in US customary units. And then delta H is the change in height. If a body goes up, delta H is positive and the delta PE is going to be positive. If a body goes down, the delta H is going to be negative and your delta PE is going to be negative as a whole. One important thing for gravitational potential energy in a rigid body system is we need to reference the center of mass of the body when determining the change in height. So if we've got some upright beam and it kind of rotates and falls like this, our delta H would be this value here. We need to measure the change in height of the center of mass. So keep that into account. Other than that, it's the exact same setup that we had with particles. Last up is linear and is elastic potential energy. So starting off with linear springs and elastic potential energy. Similar to gravitational potential energy, elastic potential energy doesn't represent an energy at all, but instead represents the potential of a spring force to do work. So as discussed with particles, the change in elastic potential energy is as follows. So delta PE is equal to 1/2 kx final squared minus 1/2 kx initial squared. All right, so with this, K is going to be the spring constant. So the stiffer the spring, the larger that number. And each spring is going to have its own separate, it's just kind of a property of the spring itself. X, on the other hand, represents the amount of stretch in the spring. This can be stretched out or compressed below the unstretched spring length. So if a spring is just sitting there with nothing holding it back, it's going to have some length. X is the difference that we have from that. So I might have X final and X initial both be values. You do want to be careful. X is not the amount of, or the difference between these two values. So you're going to have to pay attention to X final and X initial and the amount of stretch that we have in our spring. So torsional springs. So the rotational counterpart to the linear spring is called a torsional spring. And the change in elastic potential energy for a torsional spring is as follows. So delta PE equals 1/2 K theta final squared minus 1/2 K theta initial squared. So this is the same thing. So K is still going to be the spring constant. It is based on the spring that you're working with. It's a material property. And the stiffer the spring, the higher that K value. Theta is the angle of twist. So the theta is 0 at the unstretched or unloaded condition. And so as the further you stretch a spring from that unloaded condition, the greater the theta value. And we need to measure that theta in radians for the units to work out in many of these cases. So examples of torsional springs. So mouse traps, that piece right there in the center is a torsional spring. That's what's going to swing the arm around really quickly. And this is a type of spring where the theta final and theta initial are both positive values. So if you separate this spring off, it continues to unwind for a while in this. Another example is in tape measure. So there's a torsional spring. It's a different type of torsional spring in the tape measure itself. And when you kind of pull this lever back, it will pull the tape measure back into the spring will pull the tape measure back into the roll in that tape measure. All right, so that's all we've got for today's video lecture. Thank you for watching, and I hope to see you again.